Hello everyone. In this video, we will continue our discussion of the 1D motion. And previously, we talked about how to go from displacement to velocity to acceleration. And in that process, we're doing derivatives. So we have position x, okay, as a function of time. And then when we take a derivative, dx dt, we get velocity as a function of time. Okay, of course, this velocity is the x component of the velocity, which is the only component of a velocity. And then we take a further derivative, and we get to the acceleration, ax, as a function of time. And they come from dvx dt. Okay, now today we're going to talk about the opposite direction. So now suppose that you know the acceleration of an object's motion as a function of time, and then you want to calculate its velocity at a certain time. And then further on, you want to calculate its position as a function of time. Now, in mathematics, we know that the derivative, the opposite operation of the derivative is doing integral. So we expect that we're going to do some kind of integral today. The ax dt, and then that will give us the information about an object's velocity. And then if I do further integral here, vx dt integral, then I should be able to get to the position information. Okay, so that's exactly what we're going to do today. We're going to go the opposite direction. Okay, so now since we know our starting point is axt, so let's do some general discussions of what we should do with at information. And then later on, we'll focus on one special example of the 1D motion, which is 1D motion with constant acceleration. Okay, so we're going to talk about like a general ax as a function of time. And then later on, we're going to focus on some special situation, which is actually the situation we would like you to learn about. So the special one is ax is a constant in time. Okay, so that's 1D motion with a constant acceleration. Okay, so let's see how do we get from axt the information about vxt. So now let's start with diagram. Let's say we know the variation of a as a function of time. So we know this one beforehand. So now let's say the relation is like this curve. I'm going to just draw like arbitrary curve right now to illustrate the idea. And then, so we know this curve, right? So if you do the integral here, then we're actually calculating the area. So now let's say I just want to figure out some initial instant ti called ti, and then a final instant t final, and I want to figure out, let's say, the final velocity as a function of the initial velocity plus some quantity to be figured out. And this equation here is what we look for this Vx expression. Okay, so all these V's here I already get rid of the x indices. They represent the x direction velocity. Okay, so actually I can add it on. So we have x, we are x. So mathematically, we know from this definition of the ax is dvx dt. Now maybe you're not very familiar with the calculus. So the derivative here is like division. So it's like you can understand this as dvx over dt, right? Because remember the definition of the derivative. We take the limit of delta vx over delta t. Now that is a division, right? So if I multiply this dt on both sides, then I can move dt to the left side. So let's see. We have ax dt equals dvx. Okay, so now we can put the integration sign on both sides. So for the same quantity, I can integrate the same range, right? So let's say I'm looking at some initial instant, let's say it's ti, and some arbitrary instant t. So let's not call this upper bound. Let's not call it a t final, because I want to get a general expression of the v as a function of time. And then later on, if you want to know the velocity at t final, you just plug in t final here. So that's why we don't need to put t final here, although we do know the range that we're interested in is this ti to t final. Now, corresponding to the initial time, we have initial velocity, we call it vix previously. And the final velocity, again, let's not put that in. Instead, we call it vx here as some general arbitrary instant after ti. We can also have a change of the variable, especially for this dt here, because we have t to represent the final velocity. So let's call this dt prime. Okay, because the variable dt integral here, let t represent a changing variable. So that's why it doesn't matter what kind of name you call it. All right, let's call it a t prime, so that we can differentiate it from the upper bound t. Let's do the same thing here. Let's call this vx prime, so that we don't confuse it with the final velocity vx. Now for this integral, the right side is very easy because it's basically just integral over 1, a constant 1. And then that gives us vx minus vix. Okay, now the left side, we cannot do it right now because we don't actually know the ax expression. So in order to do this integral, you need to know the expression for ax as a function of time. Then you can do that integral. Okay, so right now I cannot do it, but I do know that the meaning of this integral in mathematics is the area under the axt curve. Okay, so now let's put this understanding in the picture here. So if I look at the area under the axt curve, that's axt curve, right? This curve here. So the area is basically the shaded area where I put the slashed lines. Okay, so that is the area under the curve. Okay, so you can say the change of the velocity is given by the area under the axt curve, which is this shaded area. But again, this general discussion, that's why I do not have an expression here. Okay, so now let's transition to the special case where we have a constant ax. Okay, by constant I mean it does not change with time. So reflected in the AXT diagram. Let's draw a similar one. The AXT curve is a flat line like this, okay, parallel to the time axis. And now if I want to do, let's say, starting time ti and final position t final, then the shaded area will be this rectangular area. All right, that's the area which is the shape here is a rectangle. Then the area can be calculated easily, right? Suppose I know this AX is a constant. That's the AX value here. Then the area of a rectangle equals AX, that's the height or width of this rectangle, and then the length of this rectangle is, of course, delta t, right? T final minus t initial. Again, I don't want to put t final here because I want to have a Vx as a function of time. So that's the area. Okay, and then the right side is the same as before, which is Vx minus Vix. So now there it is. We have an expression for Vx as a function of time. Okay, so let me start a new page and then write that result. So 1D motion. With a constant acceleration. Okay, so now starting point is AX is a constant, and then we just figure out that Vx is Vix initial velocities plus AX t minus t initial. Okay, that's the result we got from earlier discussion. Okay, of course, the Vix here, this one is given, right? That's given like a constant, which is also a constant. So the only variable here is this quantity t here, and ti is also a constant. It's the initial condition, right? So that's why I can actually plot this Vx. So we can have a Vx t diagram. Okay, so think about this kind of diagram. What kind of picture can we get from this relation? So first, its y-axis is Vx, the vertical axis is Vx, and the time axis is here. The origin is here, representing velocity equals 0. Okay. So we have several situations. So now let's say if I plug in, let's say ti, t equals ti. Ti is here. The initial time is here. Okay. If I plug in that, then the Vx here is Vix. So we're going to get to either here, up here. That's the value there is Vix. If this quantity is positive. Okay, so if Vix is positive, meaning it's moving along the positive x-axis, then we should get a point here. Now, the second point, I don't want to put some arbitrary value here. Instead, I want to look at this AX here. The AX here, excuse me, will represent the slope. The slope of this straight line, right? We know it's linear, so it's a straight line. If the slope here is positive, then I should have a line that goes like this because the slope ax is positive, right? So we have a line going to the right. But we can also have some kind of negative slope that will going this way, and the initial velocity can also be negative, right? So let's say the object started with a negative velocity going to the negative x-axis, then we should start with a point here, right? So let me draw all that kind of situation to illustrate the kind of picture we can get for Vx versus t. Okay, so now that will be this case here, Vix is negative, and we get initial point from Ti. And then now let's say Ax is positive, then we have a curve that looks like this. Okay, now the third one. Versus t, and then ti, and we have an initial velocity being positive. However, the slope is negative. Let's go down like that. So that's Ax negative. Okay. Lastly, we have a negative initial velocity and then a negative slope. Okay, so these are the 4 different kind of situations we can see for Vx versus t diagram. And then in the future, we're going to just take one of them to do further discussions. Okay, so let's say I want to take the first picture. Okay, so let's see. Now we have Vx versus t, where the initial velocity is positive, Ax is positive, and then the picture looks like this. It's T, Ti, Ax is positive. Okay, so let's further this discussion because I want to figure out the position as a function of time. So how do I get from here to x as a function of time? How do I get that? Okay, so let's remember the velocity's definition. Vx is dx dt. So now I'm going to do the same thing that I did for the velocities relation. So let me move dt to the left side and then do integral on both sides. Okay, and then we need some initial condition and final condition. So the lower bounds here represent initial condition. So it's Ti, start with Ti, and then the initial position here for the position x is xi. Okay, and then we get to a final position which we call the x instead of x final because we need to make it a variable, and then that's the Vx at that instant. Okay, and then we want to change the variables to prime, dt prime, dx prime. Okay, now again, the right side is very easy to integrate because it is integrand here is 1, so we get x minus xi. Okay, now the harder thing is the left side. How can I do the integral of the left side? Okay, so remember we have that expression that we figured out previously. So Vx is Vix plus Ax t minus Ti. So how about us plug in this expression to replace the Vx here? Let's see. So ti, excuse me, that was a mistake. Besides not Vx, it's actually t. That's t, okay? And then Vx here is replaced by Vix plus Ax t minus ti. And then we have an integral dt prime. Okay, and also for consistency, let's move x minus xi to the left side so that all the writings will be on the right side. So now let's see what kind of integral we get. So the first term here, Vix is a constant. So that can be integrated easily. Vix, which is a constant, so I just do the t final minus ti. Okay. Now the second integral here, because I can change the variable to t prime minus ti. So let's call it changing of variable. Of integration variables. And people do this all the time, right, in doing integrals. So you can regard this whole thing here, t minus ti, as a single variable. And then you just integrate over that variable. Okay, of course, that's a corresponding change in the integration bounds. The lower bounds now becomes 0. The upper bounds becomes t minus ti. Okay, now with that, we can integrate the second term, right? Because it's linear, so we're going to get to 1/2 ax t minus ti squared. Okay, and then you want to put in the upper bound, t equals, this one is actually t prime, so t prime equals ti, and t prime equals t. Okay, so after I substitute in the upper and lower bound, let's see what we get. Let's copy the first term, and the second term, when I substitute in t here, I get 1/2 ax t minus ti squared. And then ti minus ti minus ti here will be 0, right? So that's what we get. The lower bound will be 0. And let's copy x minus xi. Okay, so in the end, we get the following equation. So x equals xi plus Vix, which is also given. And then linear and quadratic terms. So it's a second order term, second order expression for the position x. Okay, so there is a lot of math, right? So let's understand the same thing, the same expression here from the picture that we drew earlier. Okay, so we know if I do the integral here for Vxt, this integral, okay, that's the area under the Vt curve. Okay, now let's see what's that area. I'm going to put the upper bounds here. So that will be the t, some arbitrary t greater than ti, and then that integral, right, will be this area. Okay, and before I shade this area. Let's divide it by, let's make this area, like divide this area into two different parts. So I'm going to draw a horizontal line from the initial point. And then the total area will be rectangular area here plus the triangular area. Okay, so let me write this down. So area, total area is given by rectangular plus the triangular area. So what's this rectangular area? The height is Vix, simply just Vix, right? That's the height. And the length of the rectangle is just the t minus ti, right? The difference between the two initial and final point. So that's why the rectangular area is given by Vix times t minus ti. Okay, that's exactly this term. Rectangle. Okay, now how about the triangle? We think that probably is related to the second term here, right? So let's make sure that that's the correct correspondence. So for rectangular area, we know the area formula is 1/2 the base. The base here is t minus ti. We already know that. Times the height. This height here. And this height here is the final velocity, which is Vx. That's the final velocity. Minus Vix. Okay? Because Vix is up here, and then that's the final velocity. So the difference gives us the height. And that height is exactly this term. If I move Vix to the left side, I will see that, right? So that's Ax t minus ti. Okay, so now figure out the both base and height, so we can write down the triangular area. So 1/2 the base t minus ti times the height Ax t minus ti. And that's exactly the second term, right? If I put together t minus ti, I will get 1/2 Ax t minus ti squared. So let's confirm this by writing down triangle here. Okay, and that total area is this term, this integral. So that equals x minus xi. That's exactly what we have here. Okay, so now we totally understand the quadratic formula for position, right, as a function of time. Okay, so now here comes the same thing. We visualize the velocity as a function of time for various situations, different slopes, different initial velocities, and we do the same. Let's do the same thing here. Let's say I want to visualize the x as a function of time. How can I start from here? How can I do that? So first, let me copy this x expression. T minus ti. Okay, so we know xi is the initial position, right? Initial position, it could be positive, it could be negative, but that doesn't actually affect a lot the shape of the diagram. So I'm going to just assume that all my drawings applies to a positive xi, so that I can save some space here in the drawing. Okay, I only draw the positive initial x. And here it's the initial time, ti. Okay, so first when I plug in ti, t equals ti, then the second term, third term, they both disappear. and we only have x equals xi, and that's exactly what we mean by initial position, right? Because that's the starting point at ti for the drawing. Okay. Now the curve here, Vix. If Vix is, let's say, positive, right? Let's say it's positive, then the xt, remember xt slope is the velocity. Okay, so at this initial point, that slope need to be positive, meaning it should point right side like that, right? That's the Vix being positive, so the curve should go that way, right? But now let's say also ax is, let's say, positive. Then what kind of picture should we draw? Ax is positive means that the picture here should be curving up. Remember we talked about the concavity of a curve, its relation with ax, right? Curving down or convex, ax is negative. Curving up for the xt diagram, or concave, that means ax is positive, right? So let me draw some brief note here. So these kind of diagram, curving down, ax is negative, and these kind of curve curving up, ax is positive. Okay. So now I know Vx is like that, and then I need to be, let's say ax is positive. So I need to go like that, right? So the only way I can do that is this kind of diagram. It's like that, right? So that's the ax being positive. Okay, now let me continue some other drawings. So that's x, that's t, and then that's ti. Again, remember I always fix xi to be positive. Okay. Now let's say I still have the Vix being positive. Okay, but now ax is instead negative. Let's see. We have a positive curve, slope. Sorry. But the curve need to be looking like this, right? Curving down, and the slope is like here, right? Previously, the slope should be here. Now the slope should be here. So we should have like a maxima and then go down. So here's the diagram. And that's for ax being negative. Now the third case. Ti, again, I need to do this initial position xi. And then let's change the initial velocity sign. Let's say it's negative. So I have xi positive, Vix negative, ax positive. Okay, how about that? Vix is negative means that the initial slope should be like this, right? Should be like that. And ax is positive, meaning the curve need to be going up, right? Curving up like this one. this one, right? So now we draw an initial position here, meaning I have to have an initial position here on the left side. So I can draw a curve that look like this. So there must be a minimum somewhere at some instant, and then the curve going up. Okay, so that's for where Ix being negative, Ax being positive. Okay, last situation. So again, we have a initial time, initial position. The curve need to go through this point, and then Vix is negative, meaning we need to satisfy this kind of curve, this kind of slope at the beginning. Okay. All right. So now we have to, because Ax is negative, we have to have a curve that look like this, right? And then the slope can only be on the right side, can only be here, right? So that's why I have to draw something like this going down. Yeah, sorry, I didn't have a good planning here. I should draw the point here. So however, you got my meaning, right? So the meaning is that the curve need to go down like this. Okay, so that's for Vix negative, Ax negative. So the curve is going down, curving down. And as I said, that you can also have, let's say, a negative position xi. Then all these pictures happens with a starting position on the at a lower area of the horizontal axis, and then you want to draw more on the lower side. But I want to save the space, so that's why I only draw the positive xi. Okay, so these are the four kind of situations you will see for the xt diagram. They all satisfy this relation, x equals these quadratic equations. Okay. All right. Also, let me just mention this briefly. So, in some other notation, meaning in some textbooks, they actually set ti equals 0 second. Not with x. Xi equal 0 meters. Okay, so let's see what kind of equation do we get here. Then if you do that, then the final velocity is still the initial velocity plus Ax. So previously we have t minus ti, right? So now we simply just have t here because ti equals 0. And the position now is xi equals 0, so we have 0 here, right? And then plus Vix times t minus ti, that becomes t, and then 1/2 Ax t minus ti squared, that becomes t squared. Okay, so that's why sometimes you will see these kind of equations instead of t minus ti. Okay, but again, this expression here is more general. If you do want to move ti to the origin here, then you get these equations. Okay. Now these are the two important equations in 1D kinematics. But we actually have more. So let's see. If I'm given a situation where I know, let's say, if I know, so known quantities, if I know the Ax, if I know that, right? And I I don't have any information about the t. Instead, I have v. So I know vi x, v final x. So how can I get x information? So think about this situation. So there's no time. So that means that I cannot apply this equation, right? I cannot apply this one. Instead, I have to use this final. Okay, so how about use final to solve for the time? So let's start from here. So since I know v final equals v initial x times t, so I can solve for this final time. This t actually corresponds to the final time. So t final equals v final x minus vi x over ax, right? And after that, I just plug in the second equation. So x equals vi x times t, which will be v final x minus vi x ax plus 1/2 ax times this whole thing here squared. Let's see. We can probably get some simplification here. Let's expand. Let's copy the first term. And let's expand the second term. V final x squared minus 2 v final x v initial x plus v initial x squared. Okay. Now let's see. We can probably get rid of something. So the first term vix times v final x is the same as this term, right? Except that that coefficient now is negative. So ax will cancel with one of the ax factors in the denominator, and then 1/2 will cancel with these two here, right? And then that will cancel with this. So this term disappears. These two terms disappears. And then let's see what's the remaining term. So the denominators are the same. So let me put them together, and then inside the parentheses we have negative vix squared, right? And then plus. So this term is still 1/2 v final x squared. Let's copy that. And the last term here will be positive 1/2 v initial x squared. Okay, and they can be combined. These two terms can be combined, giving us. Let's also pull out 1/2 factor because they are the same, right? So that we have v final x squared minus v initial x squared. Okay, so that's why there's another important equation in 1D kinematics. If I know or if I'm given the final velocity, initial velocity, and the acceleration a, I can still calculate x this way and through this equation. So v final x squared minus v initial x squared equals 2 times ax times x. Okay. But again, if I use my previous notation without setting x initial equals 0, then I should add x minus x initial here. Okay. So instead of x, I will write down x minus x initial here. Okay. And that will represent the displacement. So right now, this x here should be understood as the displacement of the object. And then last equation that I want to complete here, which is also important, is the following one. So the displacement is also given by the average velocity times the time. Okay, but again, in the previous notation, it will be t minus ti for the second factor here. Okay, now what is V average? V average is the so this one is it's easy to understand, right? Because it's the average velocity times the total time, and that should give you the total displacement, right? But how to understand this V average expression? I can tell you that it's simply just 1/2 the initial velocity plus the final velocity divided by 2, and then times the t. Okay, so it's the so let's say you know the initial and final velocity of an object, and you know it's a constant acceleration. Then you can safely apply this equation here to calculate the total displacement x, or the final position x. Because the reason here is because of the linear relation. So if you have v versus t that looks linear, okay, and that's the t final, and that's t initial. So this point correspond to v final x. Okay, then their average is in the middle, right, in the middle point. That's V average. Okay, the average velocity for this time interval should be in the middle, and is right at the midpoint. Here, okay? So that's why I replaced the average with this average of initial and final. So these are the 4 important equations you can apply to study various problems that include constant A, 1D kinematics for constant acceleration. All right, so now let's summarize what we discussed in this chapter. So we have a initial position, we have position, we have velocity, we have acceleration. So if you go one way, let's say this way, then you need to do derivative. But if you go the other way, then you need to do integral. A dt integral, and then Vx dt integral. Okay, and then you should be able to get all the information about this object's motion. So that way you get complete information about 1D motion. All right, so that's it. And then next time we'll see some practice problems where I will talk about some free fall example. So that would be like real life example where we have ax equals a constant, which in this case equals g, and g is 9.8 meters per square second. That's the acceleration, gravitational acceleration on the Earth's surface. And that would be like the most common example you will see that has a constant acceleration. Okay. All right. So that will be all for this lecture video. Thanks for watching.